Assalamualaikum. My name is Muhammad Muhammad Haikal. My number metric is B0921101555. This is for assignment about second order system. This is my group member. Our team has discussed and we decide to present about the robotic arm control. Background of arm robotics. Arm robotics refer to the field of robotics that focus on designing, developing, and controlling robotics arm. Robotics arm are mechanical device with multiple joints and limbs designed to mimic the movement and functionality of a human arm. These arms are widely used in various industries such as manufacturing, healthcare, logistics, and research. A control system that incorporates second-order dynamic is used to manipulate the control movement of a robotic arms while controlling it with a second-order system. The arm's position, velocity, and acceleration may be precisely and quickly controlled thanks to a second-order system. The second-order system is used in robotic arm. Control is based on the specific task requirements. The control system chooses the required position of or trajectory for the robotic arm. Commonly, Cartesian coordinates or joint angle are used to describe this position. Using the robotic arm present position and desired position as input, the control system calculates the control signal. To establish exact control over the arm movement, certain control signals were created. To compare the robotic arm current position with the desired position, the control system uses position feedback from the sensor. The control signals are produced by computing the error between the present and desired position. Second order dynamic to regulate the arm movement. The control system uses second order dynamics. This may entail the employment of method like PID, the proportional integral derivative, a popular second order control approach. To accomplish precise and responsive management of position, velocity, and acceleration, PID control modifies the control signal based on proportional integral and derivative theorem. A closed-loop operation, the control system constantly modifies the control signal in response to position feedback. This enables the robotic arm to adjust flexibly to environment change or operational disturbance. The robotic arm can obtain accurate and reliable control over its movement by using second-order system. It makes it possible for the arm to precisely follow desired trajectories, manipulate items with deft hand movement, and react swiftly to environmental change or human command. It is crucial to keep in mind that the precise control method and algorithms employed may change based on application, the complexity of robotic arm, and intent performance standards. To further improve the effectiveness of the robotic arm control system, more sophisticated control techniques like adaptive control or model-based control may also be used. Thank you.
Assalamualaikum. My name is Muhammad Fairuz bin Yasmin. I will explain about block diagram for robotic arm control. Firstly, input. This block represents the desired position or trajectory that you want the robotic arm to follow. It could be specified by a human operator or obtained from a higher level control system. Then feedback. Feedback control is an essential concept in robotic arm control. It involves measuring the actual output or state of the system and using that information to adjust the control signal, enabling precise and accurate control. From feedback, go to open loop control system for DC motor. It used in a robotic arm. The control signal is not adjusted based on the output or any feedback information. Instead, the control signal is directly applied to the motor without considering the actual motor speed or position. Next, the output goes to their ratio. The ratio plays an important role in robotic arm control by influencing the relationship between the input and output motion of the arm. It determines the speed, torque, and precision of the arm movement. Then output goes to a robot arm, also known as a robotic arm or manipulator, is a mechanical system designed to mimic the movement and capabilities of a human arm. It consists of multiple interconnected segments called link, which are connected by joint. Robot arms are widely used in various industries, including manufacturing, assembly, material handling, and research. After that, the output represents the actual output of the system, which could be the position, velocity, or any other relevant parameter of the robotic arm. It is compared with the set point to calculate the error signal, which is the feedback to the controller. Error signal, the error signal. The error signal is obtained by subtracting the feedback signal from reference signal. It represents the deviation between the desired and actual position of the robotic arm. The error signal goes to potentiometer. A potentiometer is a commonly used sensor in robotic arm control to measure the position or angular displacement of a joint. It provides feedback about the joint actual position, which can be used for various control purposes. Lastly, back to mixer symbol. The summing point where the error signal, feedback signal, and possibly other signal are added together. Next, system transfer function. In control system, the transfer function is a mathematical representation that describes the relationship between the input and output of a system. It captures the dynamic of the system and allow analysis and design of the system behavior. For a second order system, the transfer function is typically expressed in the form of a second order polynomial. The general form of a second order transfer function is gs equal k per s power 2 plus 2 zeta omega n s plus omega n power 2, where js is the transfer function, k is the function gain or overall scaling factor, s s is the complex frequency variable, where represent the real part and omega represent the imaginary part. Zeta is a damping ratio which determines the system damping characteristic. Omega n. Omega n is the natural frequency which represents the system frequency of oscillation in the absence of damping. Thank you.
Next, this transfer function represents the mathematical relationship between the input and output of the system in the Laplace domain. With this transfer function, we can analyze a design control strategy for the arm robotic system. For example, we can use a control algorithm like PID control or design robust controller to regulate the arm position or velocity based on the desired performance criteria. From the calculation, we get a peak time 0.370 and the setting time is 1.001. On the other half, we get a percentage of overshoot is 22.781%.
Next, I will explain how to using MATLAB software. Firstly, open the MATLAB, type the equation in common window in MATLAB. The graph will show. Click anywhere on the figure with the right mouse button, then choose characteristic peak response. From the menu, turn on all of the transit response capabilities. A marker denoting the peak response show on the plot. The timing and magnitude of such response are shown by horizontal and vertical dot line. Click the marker to view a data tip with the value of the peak response and overshoot. Then we need to get a data. Go to the common window, type the data equals step info, and data will show. We data will show peak time, settling time, percent of overshoot. Thank you.
Next is a value from the graph and from the calculation. We have a nearest time between the graph and the calculation. In addition, we get a 0.3454 from the graph and 0.370 from the calculation. We assume that the peak time is considered valid for both methods to calculate the peak time. The next characteristic is from the setting time. We got a 1.8176 from the graph and 1.001 from the calculation. This value shows that the setting time can assume 1 for the both calculation method. Next is the percentage of the overshoot. There are some difference for the both calculation from the graph and the calculation. The graph shown the value is 50% and from the calculation is 22.781%. This might be because on the error information key in the MATLAB. Thus, the percentage shown can assume from the calculation which is 22.781%.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Azafizi. For discussion, the most common approach for precise and quick manipulation of the robotic arms movement is to control it using a second order system. The precise control of the arm's location, velocity and acceleration depends heavily on the second order system dynamics. The capability of a second order system to deliver steady and well behaved responses is one of the main benefits of employing it for robotic arm control. Reduced overshoot, oscillations, and settling time are made possible by the second order dynamics. This is crucial when handling fragile things and conducting sensitive operations that need for exact positioning and handling. A little connection to our project involving the robotic arm control. We drew a block diagram and established the transfer function. The system's peak time, settling time, and percentage overshoot were all calculated. However, we discovered variations between the outcomes of our manual calculations and the result produced by MATLAB. The transfer function of the system was also transformed into a state space representation using MATLAB. This demonstrates that the outcome is solely determined by the system's state variables. Finally, we assess the system steady state error for inputs that were step, ramp, and parabolic. Despite the fact that the ramp and parabolic inputs displayed infinite steady state faults. In conclusion, using a second order system to operate a robotic arm offers important advantages in terms of precise and quick manipulation. The arm's position, velocity, and acceleration may be precisely regulated thanks to the second order dynamics, producing fluid and well controlled movements. The robotics The robotic arm can provide precise positioning, less overshot, and effective object manipulation by using control methods like PID control and incorporating feedback from sensors. The PID controllers, proportional, integral, and derivative term enable fine-tuning of the control signals, balancing the trade-offs between stability and rapid response. A second-order system's employment also guarantees stability and well-behaved response while minimizing oscillations, settling time, and steady-state errors. This is crucial for sensitive operations that call for careful object placement and manipulation. Overall, the addition of a second-order system to robotic arm control allows for precise, reliable, and responsive control, boosting the arm's performance and adaptability in a variety of applications. It contributes to improvement in industrial automation, manufacturing, research, and other industries that rely on robotic arm technology by enabling the execution of complex tasks with accuracy and efficiency. Thank you.